Hi class, this is Dylan Blair. In this lecture video, we're going to go through some examples on our 8.5 topics. So this is going to be if we're given two complex numbers, how we multiply these complex numbers, how we can divide multiple complex numbers, how we can take some complex number and raise it to some power n, such that n is a natural number, and also how we can find roots of complex numbers, and these roots extend beyond our principal roots, which we discussed during the lecture period. Okay, so what we're starting off with is I gave us a starting point of three complex numbers. One of them is z, the other one is w, and the last one is v. Okay, and then I also have a little bit of a cheat sheet for us, such that we know the product rule for multiplying two complex numbers, z times w. We know the quotient rule for dividing two complex numbers, z divided by w. We know the power rule for raising some complex number to a natural number n, z to the n. And we know how to reverse the de Beauvoir's theorem, where we can find each kth root, which is denoted as w sub k. All right, so if we're looking for the fifth root, we're going to have 5 roots that we're going to be looking for. Or if we're looking for the fifth root of some complex number, say z, we're going to be looking for 5 roots, and those are going to be labeled w sub naught, w sub 1, w sub 2, w sub 3, and w sub 4. And notice that we have that kind of shifting kind of property to it. So the first root is called w sub 0, and the last root is called w sub 4, even though we have 5 roots. Okay, so we count it by starting with our 0. Okay, now let's actually dive into how we can actually operate on some of these. So let's first consider, let's do z times v. Okay. Well, z times v, first what we notice is that we're going to want to get this into polar form. Okay. Well, z in polar form, let's actually sketch this out because there's no reason that you should have to memorize certain features of complex numbers, because really you can always just kind of sketch it out and figure out, okay, what is it that I need to know and how can I solve for it. So here's a real axis, here's your imaginary axis. Let's draw this first one in red. So we're going to have negative 3 square roots of 3 over 2. So let's call that, say it's going over here. That's going to be going in the real direction. And then we're going to have 3 over 2 in the imaginary direction. Okay, so we're going to have a complex number z up here. Okay, and I'm not going to bother plotting v is equal to 16, right, because that's just directly pointing in their real direction only. And if my iPad will listen to me, there we go. Maybe, there it goes. What we're looking for, in order to get this into polar form, we're looking for this theta, and we're looking for this r. And let's actually not label this r. Let's stick to our terminology. We're looking for this modulus of this complex number, which is just that length, right? So we can sketch out a triangle, and we notice, let's actually erase that modulus and put it right here. Okay. And we notice when we're solving for this triangle, really we know this side length right here. We know this height And what we're looking for is that hypotenuse. So this just comes down to using Pythagorean theorem, right? Which we know that that's what the modulus is defined as, is the square root of a squared plus b squared. But I don't want you guys to really remember it that way. It's totally up to you guys. If you guys want to remember it that way, go for it. But it's really just as simple as understanding basic trigonometry at this point. Okay. So this means that z, or modulus of z, is going to be the square root of what is our real component? It's at -3 square root of 3 over 2 squared plus our imaginary component is 3/2. We're squaring that as well. Okay. Now, squaring any negative is just going to make it positive. And then we're squaring the 3 to get a 9. We're squaring the square root of 3 to get a 3. And then we're squaring the denominator to get a 4. And we'll end up with a 9 over 4 right here. Okay, now we have, let's see, 9 times 3, that's going to be 27 over 4 plus 9 over 4. Okay, now don't need to continue to take up too much room on the page. Now we're going to have square root of 36 on our numerator. Square root of 36 is just 6. And then we have square root of 4 in our denominator, which is just going to be 2. And then we're going to end up with 3. Okay. And notice that you could have simplified the fraction inside of the square root before taking the square root. That gets you the exact same thing. All right, 36 divided by 4, that's going to give you 9. Squared 9 ends up giving you 3. And so regardless, you end up getting to the same result of 3 at the end. Okay. Now, let's look at first, kind of got a little bit premature. Let's look at alpha. We're going to say tangent of alpha is equal to the imaginary component of our complex number z over the real component of our complex number z. Okay, so this means that tangent of alpha, which is still equivalent to just sine over cosine, this is going to be equal to our imaginary component. What was our imaginary component again? It's that 3/2 over -3 square roots of 3 over 2. Okay. Now we notice these 2's cancel out. Actually, let's not cancel out the 2's, okay, because we want to manipulate this so that it looks like something that we're used to seeing from a unit circle. What we are going to cancel out is these 3's. So we can say that this is 1/2 over negative square root of 3 over 2. Okay, so this means that we're going up by 1/2 and to the left by square root of 3 over 2. So let's quickly sketch that out up here. So we're going up by 1/2 and over here by square root of 3 over 2. So our point is right here. This means that our rotation is going to be pi 6, 2 pi 6, 3 pi 6, 4 pi 6, 5 pi 6, if we were to count it out. So we can say that alpha can be 5 pi 6 plus 2k pi. So that just means that we can choose any of those coterminal angles for alpha. Okay, but we're going to end up just using 5 pi 6 anyway. So ultimately, we can say that z is going to be equivalent to the modulus of z times CIS of alpha. Okay, and again, we don't need to use the plus 2k pi. We can just choose one of the coterminal angles. So this is going to be equal to 3 CIS of 5 pi over 6. Okay, now let's do so similarly for v. The modulus of v is just simply, trying to remember what the number was, 16. So it's 16 pointing in the real direction, so its length is just going to be 16. Okay, and if you're having trouble seeing that, I highly recommend that you pause the video and kind of do the same kind of sketch that we did up here, and you'll be able to see that the length of this number is going to be directly on that real axis, so it's just going to be 16 to the right. Okay. Then we can also say that we can conclude that its angle is going to be 0 plus some 2k pi. Right? So in order to land on this real axis up here, we can rotate nothing at all and we'll land there. We can rotate 2 pi, we can rotate 4 pi, or any coterminal angle there. And again, we can just simply use any of those coterminal angles. So we can say that v is the same thing as 16 times CIS is 0. Okay. Now our ultimate goal is to do z times v. Okay, so we're going to take the two moduli, multiply them together. So that ends up being this 3 multiplied by this 16. So 3 multiplied by 16 is going to give us, let's see, that's going to be 48. Okay, and then we're going to have CIS of 5 pi 6 plus 0, which is just going to be 5 pi 6. Okay, now that would be our answer. Now, I'm going to show you guys something else. Okay, and we'll go through the same proof when we multiply two other numbers as well. Okay, because sometimes it's a little bit easier. Like, you do not have to always be in polar coordinates in order to perform these operations. Like I showed you guys in the lecture notes, you can find the roots without being in polar coordinates, right? But it's much easier to be in polar coordinates. Same goes for multiplication and division. You don't necessarily have to be in polar coordinates, but sometimes it's easier. In this case, it actually is not, and I'm going to show you why. So, let's say this is OR. If we have z times v, this is going to be equal to whatever that z was. I don't remember what z was again. That's right, it is negative 3 square root of 3 over 2 plus 3 over 2i, and we want to multiply this by 16. Okay, now we just notice we just have some number that's going to be distributing through to each term. Okay, so that means that 16 divided by 2 is going to give you 8. 8 times 3 is going to give you, let's see, that's going to be 24. So we're going to have negative 24 square root of 3. Okay, then again, we'll have 3 times 8, which is going to be plus 24i. Now the difference between these two answers is that this one is your polar representation, and this one is your Cartesian representation of the exact same number. Okay. Now, I'm going to leave it up to you guys to show that these are equivalent, but they in fact are. And you notice doing the multiplication here took us arguably 2 lines. We could have really done this in 1 line, right? We could have just looked at the 2 numbers and said, oh, I just have to multiply 16 by both of the numbers, and written down your answer. Then you're done. Okay. Now, let's consider, let's do z times w. Okay. So if we were to do z times w, oh yeah, and note, if we were to, let's do a different color here. If we were to do like something like 2z, where we're just scaling some number, which is in essence kind of what we did here. We just have 16 multiplied by the other complex number. So we could think about this 2 is just modeled as some complex number, but really we're just scaling this complex number. So we can say 2z is just the same thing as multiplying 2 by each of these, so that we could say this is going to be negative 3 square root of 3 plus 3i. And then that's it. Okay. So in essence, if you were to have some question that was like 2z divided by 3w, you just need to scale 2z to get some new numerator and scale 3w to get some new denominator. You can then convert the results from those two into polar coordinates, because trust me, when you're doing division or quotients, quotient rule is by far the easiest. So definitely always convert there. But either way, you can then convert both the results, so your numerator and denominator, the 2z and the 3w, into polar coordinates, and then you can use quotient rule, which is just listed up here above. Okay. Okay. Either way, now I'm off my tangent. Let's move on to the next example. So we're going to be multiplying z and w together. Let's first do it our Cartesian way. And it really always matters too, like if the answer is asking for it in Cartesian coordinates, then there's really no reason to convert this into polar coordinates, perform the operation and then convert it back. If you understand how to do these multiplications without converting. But if it's asking for it in polar coordinates, you might as well just convert it into polar coordinates, do the product rule, and then you have your answer already. But it's really up to you. I'm just kind of giving you guys both examples so that you can see both, to have both tools in your tool belt. Okay, so we're going to have negative 3 square root of 3 over 2 plus 3 over 2i. And then we'd have 3 square root of 2 minus 3 square root of 2i. Okay. And also note, when you do just straight up multiplication of these in Cartesian coordinates, sometimes this is a little bit trickier. Okay. Because we're going to have to distribute this term to this term and multiply it. So we're going to have negative 3 square root of 3 over 2 times 3 square root of 2. Okay, so we're going to have the 3 times the 3. So we're going to have this negative 9. And then we'll have square root of 3 times square root of 2. So we'll have square root of 6 over 2. And we're going to have to distribute it through to this term. So we're going to have plus, because negative times negative gives us a plus. 3 times 3 gives us 9. Square root of 6 over 2. Now we have this I floating around. Okay. Now let's move this down one line. Then we have to distribute this term to this guy. So we have 3 over 2 times 3 over 2i times 3 square roots of 2. So 3 times 3 is going to give us a 9 square root of 2 over 2 I. And lastly, we have to distribute this term. Okay, so we have a positive times a negative. So we're going to have a negative. We have 3 times 3 is going to give us 9. Square root of 2 over 2. But now we have this I squared term. Okay. Well, I squared, remember I is equal to the square root of negative 1. So we're taking the square root of negative 1 times the square root of negative 1, right? I squared is the same thing as I times I. So square root of negative 1 times square root of negative 1, the square roots cancel out and you're left with negative 1. Okay. Now another side note. We have the square root of 6. And does that... Oh, never mind. That doesn't simplify any further. Did I do something wrong? No, we're good. It just looks kind of funny. But that's okay. But in terms of for when you guys, if you guys are showing that the two are equivalent, I am going to make the simplification. It doesn't really matter if you make the simplification or not. It doesn't really change your answer. But I want to be able to group these two together, these two like terms of i's together. And in order to do so, I want the square roots to be alike. Okay, so I want to be able to have some square root of 6. Okay, so in order to group some square root of 6 in there, that means that I want to pull out, essentially, I want to have, I want to put in a square root of 3 in there. So I essentially want to put in a square root of 9 over 3, right? Because the square root of 9 over 3 is going to be 3 over 3, which is going to be 1, right? And it's not quite what I was intending to do. Give me 1 second. You know what? Ignore that. It's going to make it too complicated. I thought it was going to be simpler. But it's not going to be as trivial for you guys to see when you do the multiplication in Cartesian versus the multiplication in polar coordinates. It's not going to be as easy to see that they're the same. But either way, so from this negative 1 simplification, we can then see that this goes to a plus 9 square root of 2 over 2. Okay. So now when we group everything together, we'd have 9 square root of 2 over 2 minus 9 square root of 6 over 2. And these are our real components. So this entire parentheses is like your A. And then we're going to have plus 9 square root of 2 over 2 plus 9 square root of 6 over 2 multiplied by I, and those are your imaginary components, right? So this entire thing is like your B. And that would be your entire answer. Okay. Now it's not too bad. It probably doesn't look that bad watching me do it. But in terms of when you guys go to do it, it sometimes can be a little bit tricky. Okay. So now let's do it the polar way to convert it into polar so that we can perform the product rule. So we've already solved for z in terms of polar, and that was above. We had said, what was it again? We had said that was 3 CIS of 5 pi 6. Okay, now I'm quickly going to solve w. So w is going to be the modulus of w times CIS of beta. Okay, well, the modulus of w is going to be equal to the square root of our real squared. So 3 square root of 2 squared plus our imaginary squared, negative 3 square root of 2 quantity squared. So 3 squared is going to give us 9, and then square root of 2 squared, the square root cancels out, so we're left with a 2. So we get 9 times 2, which gives us this 18. And then we're, whoa, I don't know why that zoomed out. I actually kind of like it right there. We can see more. Either way, we're going to get the exact same number, plus 18. Okay. Now 18 plus 18 is going to give us 36, so that we end up with 6. Okay. Now, this last, or the next one, we need to know what beta is. So we know that tangent of beta, which is equivalent to sine of beta over cosine of beta, is going to be our imaginary. So negative 3 square root of 2 over our real 3 square root of 2. Now if we were to cancel out these 3's and then divide by 2 on both sides, this is equivalent to saying negative square root of 2 over 2 over square root of 2 over 2. Okay, so we're really just looking as we're going down by negative square root of 2 over 2 and to the right by square root of 2 over 2 until we end up right here. And we can say the angle that gets us there is equivalent to negative pi fourths. So we can say that beta is equal to negative pi fourths plus 2k pi. Okay. Now once again, we can just take one of these coterminal angles, which would be negative pi fourths. Okay. So we can say, oops, did not want to change colors yet. We can say that this in polar representation is going to be 6 CIS of negative pi fourths. Okay. So now ultimately, when we're finding z times w, it's going to be the two moduli multiplied by each other. So 3 times 6 is going to give us 18. And then we're going to be adding the two angles together. So 5 pi 6 plus a negative, which is the same thing as subtracting, pi fourths. Okay, in order to simplify those angles, we're going to need to get a common denominator, which is going to be 12. So we could say 10 pi twelfths minus 3 pi twelfths, so that we get 18 CIS of 7 pi twelfths, which in fact is a weird number. Right? It's kind of what we expected, because it looks weird in Cartesian coordinates, and it also looks kind of weird in polar coordinates, because that's not an angle that we're used to seeing in our unit circle. But that's what it would correspond to. It would correspond to these numbers if we were to actually work them out. Okay. Now let's very quickly, because it doesn't really change much, let's very quickly talk about if we were to take z divided by w. So if we were to say we wanted to take z divided by w, the only difference is that we're going to take our modulus of z, divide it by the modulus of w, and then we're going to take CIS of alpha minus beta. Okay, so the modulus of z is going to be 3, the modulus of w is going to be 6, alpha is 5 pi 6, then we're taking minus negative pi fourths. Okay, so that we end up with 1/2. And again, we can just take those results from our alike denominator from above, so 10 pi twelfths plus 3 pi twelfths, so that we can say that this result is 1/2. Oops, completely forgot the CIS. So CIS. So we'd have 1/2 CIS of 13 pi twelfths. And that would be your answer for taking the complex number z and dividing it by the complex number w. Okay. Now, lastly, another quick one before we get to finding our roots. If we were to take z to the 50th power. And how long are we on our video is kind of long right now, so this will be the end of the video on this example, and then we'll have a separate video for our roots. Okay, so if we're taking z to the 50th power, this is going to be taking the modulus of z to the 50th power. And what was the modulus of z? That was 3. Okay, 3 to the 50th power. And we're not going to simplify that, but this is the same thing as taking 50 times alpha on our inside. So we could take, this is 3 to the 50th power. I'm not going to simplify that, but we're going to take CIS of 50 times 5 pi 6th. Okay, now we can simplify that before we start multiplying across, right? So we know that 50 and 6, those are going to go in twice. So we'll have 25 left over and 3 left over. And then 3 doesn't go into 25, so that's it that we can simplify that to. And so we can say our final answer would be 3 to the 50th power times CIS of 25 times 5, which is going to be 125 pi thirds. And that would be our answer for taking our complex number z and raising it to the 50th power. Okay, and as I mentioned, that is it for this lecture video, and I will see you guys again here in a second for finding roots.